All right, yesterday we were talking about one-sided limits, and we were talking about when a limit exists. Today we're going to talk about something called continuity. But before we get into that, let's just review what we learned yesterday. And we know that a limit exists if the limit from the left, so the limit as x approaches a from the left-hand side of f of x, is equal to the limit as x approaches a from the right-hand side of f of x. All right, we were calculating left-hand limits, right-hand limits, and in order for the limit to exist at this specific a value or the specific value of x, then both of these things have to be the same. If the limit as x approaches a from the left was -1 and the limit as x approaches a from the right was +2, then the limit would not exist as x approaches a. What I have here also are a picture of three graphs, what are said to be, we call these continuous functions. All right, the reason they are continuous is because they have limits that exist at every x value. Right? Most of the functions we've looked at up until this point, okay, would be continuous functions. In order for something to be continuous, it has to meet three specific requirements. Okay, we know the first is that f at a is defined. That means the function is defined at that x value. All right, the next thing is that a limit exists as x approaches a. So not only is it defined, but the function also has a limit, also has to have a limit at that x value. And finally, the third thing is that the limit is actually equal to the defined height. So the limit as x approaches a has to equal f at a. In plain English, it reads like this. The graph must be defined at that x value, a limit must exist at that x value, and the limit must be the same as the defined height. So steps 1 and 2 must give you the same value. And this is like a hierarchy of the way you tackle these. So you would check step 1. If it meets that, move on to step 2. If it passes step 1, fails step 2, you can stop. You don't have to go to step 3. Or if it fails step 1, you can say it's discontinuous at that x value because it's not defined there. In plain English, we say a function is continuous if there are no holes or no breaks in the curve. And what that means is you'd be able to draw the curve without lifting your pencil. All right, so let's have a look at this example right here. Now, in order for this to be continuous, I would have to be able to draw this curve without lifting my pencil. Okay, well, you can see that I'm going to have to lift my pencil here. Yes, some people might argue that, oh, well, Mr. Carter, if you just go around the horn here and come back around, okay, we're not going to get into being that technical. This represents a hole in the curve, all right? That point, that curve doesn't exist right there. So in order to go from here to here, I'd have to lift my pencil. All right, it's more obvious that I have to lift my pencil at this x value. Okay, look, I'm way down here, and now in order to get up to that piece of the curve, I'd have to lift my pencil and start up here. Again, I'd have to lift my pencil here to draw that piece. So we can see that this function is actually discontinuous at a couple, or actually 3 x values. First being, it is discontinuous at x equals 1 because it breaks that first rule, okay? F at 1 is undefined. There is no closed dot, no solid dot when x equals 1. So if I go over to where x equals 1, all right, f at 1 is an open dot, means it's undefined there. That would mean the function is discontinuous at f at 1, or when x equals 1. It's also discontinuous at x equals 3. The reason being is because the limit as x approaches 3 of f of x does not exist. Okay, why does it not exist? Well, this goes to our lesson from yesterday. Okay, look at, if I approach 3 from the left-hand side, so yesterday or in our previous lesson, the limit as x approaches 3, if I want to figure that out, I'd actually have to put up a little straight edge here where x equals 3, and I'm going to approach 3 from the left-hand side. I arrive at a height of negative whatever, something down here. If I approach 3 from the right-hand side, you can see that I'm arriving at a positive height. Well, I don't arrive at the same height from the left as I do when I approach from the right. Therefore, the limit as x approaches 3 does not exist. And that would break the second requirement for continuity, right? In order for the function to be continuous, the limit has to exist as x approaches this x value of 3. And finally, the last point of discontinuity would be when x equals 5. All right, it's discontinuous as at x equals 5, but for a different reason. That is, the defined height of the function, this height right here, does not equal the limit as x approaches 5 of f of x. If I ask you what the limit would be as x approaches 5, look at, when I approach 5 from the left, I arrive at this hole. When I approach 5 from the right, I arrive at this hole. The intended height of the function, or the limit, would be this hole, whatever height that happens to be. Okay? F at 5, the defined height, is way up here. Those two things are not equal. So if I go back to our properties of limits, or our requirements, sorry, our properties of continuity, the requirements that have to be met are the following. It has to be defined, a limit has to exist, and the limit is actually equal to the defined height. Undefined, no limit, and the defined height does not actually equal the limit. If I go full screen on this, you can pause it, and there's a formal definition of why it's discontinuous at 1, discontinuous at 3, and discontinuous at 5. So you can pause the video to read that. All right, let's look at an example of what we might see when we're working with continuity, or a question involving continuity. And we're going to explore this piecewise function down here. But first and foremost, I'd like you to kind of highlight this. I mentioned it a few moments ago. That's all right. All right, fire this right here. The struggle is real, folks. All right, if you have to lift your pencil from the page to sketch the graph, it is discontinuous anywhere you lift your pencil. So in order to figure out if this is continuous or not, I could actually sketch the curve. All right, but part A, it's not actually asking me to sketch the curve first. It wants me to determine if it's discontinuous just by looking at this. Well, remember those 3 requirements. And first of all, let's try and figure out where are the possible points of discontinuity. Notice this piecewise function, it actually has 4 pieces. All right, it switches from the function 3 minus x, this linear function, okay, to this other linear function. That this piece would just have a height of 4 the whole way, but it switches at an x value of -1. Okay, so that's one of the points, or one of the x values that we're going to have to test. The other one would be 2, okay, because it also switches from 4 to 1 at an x value of 2, and from 1 to 8 minus x squared at an x value of 2. So there's something going on at -1 and +2. So let's just check those. So for starters, we'll go with -1. All right, I want to find what the defined height of the function is when x equals -1. Well, check this out. I have these two pieces of the curve where the -1 is involved. The defined height of the function is where x actually equals -1. That would be this section right here. Okay, up here it just says x is less than -1. Okay, so x wouldn't equal -1 on this portion of the curve. X can equal -1 on this portion of the curve. So f at -1 would actually equal 4. I'm just looking right here. There's not really anywhere to plug the -1 in. It's telling me that the height is always 4. Okay, so it is defined. Check. Move on to step 2. All right. Let's try and find the limit as x approaches -1 from the left of f of x. Okay, that would equal the limit as x approaches -1. And what portion of the curve would be coming from the left-hand side? Well, that'd be this portion of the curve, because these values, x is less than -1. Those are x values that are just that, less than -1. We would be coming from the left-hand side of -1. So like numbers like -2, -1.5, -1.25, -1.1, and so on. But in order to determine that, I have to use this equation, 3 minus x. With some direct substitution, this becomes 3 minus -1, which gives me a positive 4. I'm also going to check the limit as x approaches -1 from the right of f of x. Now keep this in mind. We want to be approaching -1 from the right-hand side. So I have to look to this portion of the curve. All right, these numbers right here would be to the right of -1. That's saying like between -1 and +2. All right, so those numbers are on the right-hand side of -1. There is how we define that curve where x value is between -1 and 2. Nowhere to put a -1 in there. That's always at a height of 4. Okay, so the limit as x approaches -1 of f of x is going to equal 4. How do I know that? Because the left-hand limit is 4 and the right-hand limit is 4. Okay, if these two things are the same, the limit does exist. Finally, step 3. Does step 1 equal step 2? Does the defined height of the function, f at -1, equal the limit as x approaches -1? Well, yes, they're both equal to 4. So we could say f at -1 equals the limit as x approaches -1 of f of x. It satisfies all 3 requirements. That would mean it would be continuous at x equals -1. All right, I'm going to erase all of that. Now I'm going to do the same thing with a +2. So if you want to kind of take a minute and pause that to get that down, by all means do so. Now I'm going to do the exact same thing, only this time I'm checking +2. I'm checking for continuity at +2 because that's another x value where the function switches. All right. Let's find f at 2. Well, we got to find out where the function is actually defined when x equals 2. That's this portion here. Right here, it just says less than 2. Here it says greater than 2. So it doesn't equal 2 on either of those. But it does equal 2 on this portion. All right. And again, there's nowhere to plug any x, no formula here. It's just telling me that when x is 2, y is 1. So the defined height of the function would be 1. Step 2, find the limit as x approaches 2 from the left of f of x. Which portion of the curve is to the left-hand side of 2? All right, it would be numbers that are smaller than 2. This one right here. So it equals the limit as x approaches 2, and that would equal 4. We're talking about this portion of the curve. Now we got to find the limit as x approaches 2 from the right of f of x. That would be this portion of the curve. These are numbers that are greater than 2. So I would be coming from 3 down, so 5, 4, 3, back towards 2. All right. And this one requires a little more work, but not much. I'm just going to plug a 2 in for x and square it. 8 minus 2 squared, 8 minus 4 is 4. Okay, so the limit as x approaches 2 of f of x would equal 4. How do I know that? Because the left-hand limit as x approaches 2 is equal to 4, and the limit as x approaches 2 from the right is 4. Those two things are equal. We have a limit there. So the function is defined at an x value of 2. It has a limit at an x value of 2, but it breaks property number 3. Okay, the defined height does not equal the limit. So I can say f at 2 does not equal the limit as x approaches 2 of f of x. Does not equal. Okay, therefore, it's discontinuous at x equals 2. So it was continuous at x equals -1, discontinuous at x equals 2. Part B of this question actually asks me to sketch the curve. All right, you would have gone through this probably in a previous course, but I'll quickly go through it with you. And you can see why it's discontinuous. I'll darken that up a little bit. All right, so how this works is that like this. I broke this up into 1, 2, 3, 4 pieces. The first piece was defined by, or sorry, was given the equation 3 minus x. That was for x values less than -1. So I use -1, -2, -3, -4. You might ask, well, why'd you put a -1 in there if it can't equal -1? Notice how I excluded -1 by putting an open dot. You're right, it can't equal -1, but it could be negative 1.1 or negative 1.01, or if I just start at this first point, I'll be missing this gap right here between all the x values between -2 and -1. Might not seem like a lot, okay, when we're thinking in terms of whole numbers, but it is a significant portion of this curve. All right, so how do I exclude the -1 with an open dot? How did I get these y values? I plugged a -1 in for x. 3 minus -1, positive 4. 3 minus -2, positive 5. 3 minus -3, positive 6. 3 minus -4, positive 7. And I could have kept going. I just put an arrow to indicate that it goes left forever. It's this horizontal section, sorry, this linear section right here. All right, and that is an open dot right there at -1, 4. However, you'll notice on this next section, all right, that open dot actually gets filled in. Why does it get filled in? Well, the next portion of the curve goes from -1 to +2. It can equal -1. It can't equal +2. So I went from -1, 0, 1, and 2. Again, how did I exclude the 2? By putting an open dot. Notice that for all of these x values, the height of the function is 4. That's this horizontal section. Closed this dot was open at -1, 4. Now it's closed. So look, you can see it's actually continuous all the way up to here. There's that open dot. Okay, this next portion of the curve says when x equals 2, y is 1. That's simply one dot, one point. And that's this little point right here, 2, 1. 2 to the right, up 1. I don't join it to the other pieces, okay? It's kind of floating out there on its own. And finally, this last portion of the curve is this parabolic section. It's a parabola or a quadratic. It's for x values greater than 2. Greater than 2, I'm talking 3, 4, 5, 6, 7, and so on. Notice how I put a 2 in the chart. I excluded it by using an open dot. 2, 3, 4. When you put a 2 in for x, 2 squared is 4. 8 minus 4 gives me 4. When I put a 3 in for x, 3 squared is 9. 8 minus 9 is negative 1. When I put a 4 in for x, 4 squared is 16. 8 minus 16 is negative 8. So I've got the point over 2, right 2, up 4. It's an open dot on top of an open dot, so it remains open. Remember this, if you put, oops, I just filled it in by accident. If you have open dots on top of other open dots, they remain open. If you have closed dots on top of open dots, they're closed. Case closed. Okay, 3 comma negative 1, that's 3 to the right, down 1. 4 comma negative 8, that's 4 to the right, down 8. And I tried to join those as best I could. Now, after drawing the function, you can see that the function is discontinuous at x equals 2. This diagram proves what we solved up here. We said it was discontinuous at x equals 2 because the defined height of the function, f at 2, did not equal the intended height of the function, or the limit as x approaches 2 of f of x. There were two different heights. This one was 1, this one was 4. The picture shows that. Discontinuous at x equals 2. I can't draw this curve without lifting my pen at this x value. What is that x value? That's an x value of 2. So we say it's discontinuous at x equals 2. So I go full screen on that. There it is. Okay, that should help with your assignment.